I'll start by talking about how we know what we know. How do we even measure past climate change? One of the most, I think, well-known examples is ice cores. Has anybody here heard anything about ice cores before? Yeah, a lot of people. Ice cores are very popular in Boulder because people here like snow and ice. So I really appreciate that. So the way that those work, for those of you who don't know, is that snow falls and it accumulates in layers through time. And then you can walk out onto the ice sheets in Greenland or Antarctica, or you can go to glaciers on the tops of mountains. You can basically stick a tube, not a tube, something like a tube, into the ice, pull out a core. But what do you need in order to look at ice cores? You need ice, right? So as a tropical climatologist, that doesn't really help me very much. There are tropical glaciers. There are great ice core records for Mount Kilimanjaro, for example. But we need more than that. The other thing, too, is if we want to look at very long timescales, ice, while it is wonderful, it melts. As I look instead at mud. Or we call it mud. Yes, you heard me right. MUD, mud. We call it sediment. That is its more technical term, right? So I look at sediment that collects at the bottom of the ocean, or it collects at the bottom of lakes. And what that essentially is a huge repository of everything that washed into that lake, settled out at the bottom. It's also a repository for organisms that lived within the lake, lived and died, decayed, settled out into the bottom. And so just like an ice core, we can take a boat out onto a lake, we can punch a hole in the mud, pull out very long cores. And what we end up getting is old mud at the bottom, younger mud at the top. We can radiometrically date that mud. And we can do all kinds of chemical analyses. We can look at the chemistry of the mud. We can look at clay minerals that have been washed in. We can look at minerals that have been blown in. We can look at fossilized pollen grains produced by trees and grasses around the landscape. We can look at particular organic molecules, which is what I really focus on, biomarkers, which are indicative of certain types of plants living on the landscape and tell you all kinds of information. Lake Malawi's been around for probably more than 1 million years. So it's been sitting there on the landscape. Its lake level has been fluctuating a lot. And the sediments record that. Those layers are really nice and preserved very intact. And that's because Lake Malawi today, because it is 700 meters deep, has a layer at the bottom that has very little oxygen in it. So there's not a lot of critters in there to burrow through the mud and mess up the nice laminations that we have. Very different story is this other picture here, this one on your right. This is indicative of a low lake level. Most of that mud is composed of calcium carbonate, and that means that the lake level had dropped so much that all the calcium ions and the bicarbonate ions floating around were able to fuse together, form calcium carbonate, and settle out and get deposited in the sediments. We also see really no nice layers in that particular sediment, and that's because the lake had dropped to such a low level that the bottom waters were very oxygenated. And so there were little critters around who could start moving around in the sediments and messing up our nice, pretty laminations. Lake Malawi is actually a really cool example because that gray blob of sediment that's in the core on the right that you have there in that handout was deposited during what we call a megadrought. This is again a sort of confusing term, a way that geologists are confusing everyone. When meteorologists say megadrought, they mean the 1930s Dust Bowl, right? When we say megadrought, we mean something that lasted 10,000 years or longer, really, really long. So this is for lakes. The same thing applies to the marine realm. And marine cores are really fantastic because they can go back tens of millions of years or even further. Marine mud has been there for a really long time, and we can take advantage of that. So we can apply a lot of these same tools, and we can apply other tools, and we can start to look at how the global carbon cycle has changed, for example, over time. So this is really where most of our knowledge comes from. When we talk about very long-term changes in climate, not short-term like we're seeing today, but long-term changes in climate.